Okay, so this is Mohammad Qasim from Team Pakistan, and I'd be presenting the problem burning bottle cutter. Okay, so this is our problem statement, and I believe that the host has read it. I just show you this GIF over here, and if you can see this, and then I'll move to our interpretation of the problem. Okay, fine. So our interpretation was to first explain the phenomena, then optimize the procedure, and then the possible design variations. So coming to explaining the phenomena, we had to look into two things: the thermal shock and properties of glass. So what is thermal shock? It is the mechanical load caused by rapid change in temperature, that is temperature gradient. What this does is that it causes uneven expansion and contractions in a medium, and this develops stress that leads to a fracture. This is the picture from our source. You can see. So coming to the fracture conditions, the fracture condition should be that the tensile strength should be much lesser than the stress induced, and stress is directly proportional to the Young's modulus and the coefficient of thermal expansion. If you look at this equation, the stress is also directly proportional to the temperature difference. If you look at this equation, the only variable here is the temperature difference, and other parameters are constants and dependent upon the material. And so most of our work was around the single variable. So the properties of glass, we're coming to properties of glass, is a poor thermal conductor. It has non-uniform transfer of heat, and expansion in it occurs non-linearly, and basically that is why we get the fracture. So coming to the specific properties of glass, glass is low tensile strength, high elastic modulus. It has relatively high coefficient of linear thermal expansion, and minor temperature difference can lead to fracture. So if you recall, these properties are in accordance with the fracture condition, and so this makes glass an adequate material to get the fracture due to the thermal shock. Now, if you come to this picture and if you look at this diagram, which is labeled compressive, this is our case. The TP is the surface temperature and TZ is the core temperature. We light the surface, so the surface temperature rises and becomes hotter than the core temperature. And this produces this delta T. You see the temperature difference. And when we put the whole system into the temperature difference is exaggerated, and thus this leads to the fracture due to thermal shock. Okay, so optimization part. The goal is to maximize the temperature difference and localize the heating provided by the string to get a cut that requires the least smoothing. By smoothing, what we mean here is that once the bottle is cut, we would need to smooth it either through a sandpaper or any other tool. The cut that requires the least smoothing would be smooth, and the cut that requires more smoothing would be rough when I'll be using these terms. So that's what I'll be meaning. And beneath you can see the. So coming to optimization parameters, we had fuels, material of string, number of loops, burning time, and temperature of water. So the two fuels we used were the acetone and methanol. You can see the temperature difference between them and the burning time and the orientation. What we mean by angle here is that the flame of acetone was too low and the temperature too was too low. So what we had to do was we had to incline the bottle so that the heat could be localized, so we could get a cut. But this was not case with methanol because the flame was well enough spread, and the heat and the temperature too was good enough to give us a cut on both sides. So conclusion: in the cut occurred approximately 0.4 to 0.6 centimeter away from the string. Quality of fuel is directly related to the quality of cut, and methanol was the better fuel. Material of string, we used 5 materials, each of 60 centimeter length. So to check the fuel absorbed by each material, what we did was to immerse the strings in fuel for 1 minute, and then we pulled out the string, and then we squeezed it, and then we measured the squeezed alcohol. Basically, we squeezed it into a dry and empty container, and then we measured the squeezed alcohol, and we got the absorbed fuel. And for observation, we observed the flame that it produced and whether the cut was given or not. So three strings gave cut. The cotton cloth, the cut was rough. The thick cotton string, the cut was smooth. And the fiber rope, the cut was the smoothest. The fiber rope gave the smoothest cut. But the thing is that since we had a limited amount of fiber rope, the further experiments we conducted were with the thick cotton string. Okay, so this optimization is dependent upon the material of string. For the fiber rope or the cotton cloth, only one loop would have been more than enough to get the bottle cut. But since our material didn't have, sorry, I skipped. This is the conclusion for the material of strings. The quality flame is dependent upon the material of string, and the absorption is directly related to the burning time. So keep that in note. Okay, so number of loops. The number of loops is dependent upon the material of the string. So for the cotton cloth or for the fiber, of one loop would have been more than enough to get the bottle cut. But since our chosen thread didn't have that good an absorption, so we had to get an optimum number of loops so that we could get we could get a good cut. And over here, you can see the pictures for 1 loop, 2 loop, 3 loop, 4 loops, and 5 loops. And in conclusion, 4 loops work best for the thick cotton string. Again, this is dependent upon the type of material. Okay, coming to burning time, the intent here was to get the least burning time for methanol and the thick cotton string, at which we would get a cut, and also to see how the smoothness of cut varied from time to time. Fuel was methanol, the string material was thick cotton, number of loops was 4, and water temperature was 27 degrees Celsius, which was the room temperature. And for our observation, at least 25 seconds burn time is required for methanol and thick cotton string, and 25 seconds cut was relatively smoother than 40 seconds cut. So in conclusion, the lesser the burn time, the more localized the heat and smoother the cut. Coming to water temperature, okay, so we used the already cut bottles for this experiment. The water temperature was varied, the burning time was kept constant at 30 seconds, and the type of string and number of loops were also kept constant. For the observation, the reused bottle didn't cut at the burning time, which did cut the unused bottles. The glass merely cracked over 10 degrees Celsius. So we got a crack at 3 and 5 degrees Celsius, which a crack and the bottle broke upon a mild hit. And upon 10 degrees Celsius, we got the bottle cracked. And upon 15 and 20 degrees Celsius, we merely got the bottle even cracked. So in conclusion, the heating strengthened the bottle because the bottles weren't getting cut on conditions which would usually cut the unused bottles. So this showed that the temperature had strengthened the bottles. And this isn't something new, to be honest. There is glass tempering, and there's tempered glass, and there is a thermal strengthening of glass. So it's only natural that the heat did strengthen the glass in those bottles. And the best temperature range for methanol and for the thick cotton was from 0 to 10 degrees Celsius. So for design variations, the spread out designs are favored. As you can see in the pictures, you can see that the crests and troughs in these designs are quite spread out. So so it could have been a square wave, or it could have been a triangle wave, but then the heat wouldn't have been too low. We wouldn't have gotten a cut that was accordance to our string design. So as long as the design was spread out, in our case, we did get the cut according to our design. But again, it required a lot of smoothing, and it was basically a rough cut. So in conclusion, the best bottle cutter would be which provided targeted heating. It had a short burning time, it had high intensity flame, and it had freezing cold water. Okay, our limitations: we had limited variety of fuels. We did have the possibility of petrol, but it was too dangerous. And then we had the possibility of the lighter fluid, but we couldn't get it out of the container because the container was pressurized, and the container basically exploded twice. So we were only limited to 2 types of fuel. We also had a limited variety of strings. We only used 5 strings. There was also a limited variety of the thickness of glass because the most glass was of the same. Because the most glass we could find in our local markets were mostly of the same thickness. So that too was a limitation on our ends. And there was also no means to measure the temperature of the flame. So that was a big hurdle for us. Okay, that's it from our side. Thank you.
Thank you, the reporter, for your presentation. So here is our opposition. So the problem statement states that it is possible to cut glass bottles into 2 pieces with a string using fire and cold water, and asks what is the physics behind this effect and how one can optimize it, and is it possible to cut a shape in a glass that's more complex than a simple straight line. So the presenter presented a simple theoretical model of a phenomenon. He mentioned the thermal shock needed, the uneven expansions in the glass, which fracture conditions, are needed for the fracture, He did mention some properties of the glass. Then he used a lot of optimization parameters, like maximal temperature difference, fuel liquid, different liquid fuels, different strings, different number of loops, material thickness, burning time, heat localization. He did mention water temperature and some design variation. Okay, so key points of the problem was to propose the physics behind this phenomenon. So the presenter mentioned the thermal expansion that is the key point of this physics of this phenomenon, and of course also the low thermal conductivity of a glass, and presented some properties of the glass. However, he did not really quantify the glass he was using for his experiments, like the density of the glass, molecular structure, and the type of glass. And if in the video there was a flame only on one small side of the whole parameter of the glass, and if we are concerned if the temperature is the same on the whole parameter, then about the optimization of the process, he used a lot of parameters and tried to optimize them, like maximum temperature difference, different fuels, material strings, number of loops, and water temperature. We are wondering about the scaling and the size of the bottle, which parameters he did not use, and also the imperfections of glass, like cracks, bubbles, or something like that, which could be important in the cracking of the glass. And also another parameter of the glass he did not mention is the thickness of the glass he used. Then he proposed a design variation to cut a more complex shape out of glass. Although he did mention to cut a shape that wasn't a straight line, the cut was relatively rough and it required smoothing. And he did not try different shapes. He did try this wavy shape, but otherwise it his experiments like some control, and that parameters could be more strictly presented. Okay, so I would like, in discussion, I would like to discuss different types of glasses and different glass parameters like thickness, molecular composition, and type, and how these parameters affect the cracking of the glass. We are concerned about the some additional cracking before heating, which could be beneficial in the this more complex structure, and what could be the biggest curvature in theory, and how could this be approximated?
First go through the types of glasses. I did mention this in our limitation that we didn't have that quantity of glasses. So that basically what happened was that the glasses we found that were thick weren't of the same design or of the same radius, and otherwise basically to conduct experiments we need to keep all the other parameters constant and only one thing needed to be varied, right? So they were mostly, if we did go for different types of glasses, they won't be having the same design. So the bottle that we found of the same design were of the same thickness, and that is one of the limitations over here, that we couldn't go for the types of glasses.
But
Other
sorry, and what do you think the different thickness would, how would different thicknesses affect this cracking?
Okay, so the thickness that we tried, we did one or two bottles did have a greater thickness, but we obviously didn't add that to our data because they had different shapes. So what happened there that it required a greater burning time because the temperature difference between them wasn't being built up at the time that the thinner bottles could get built up, and also obviously the quality of flame did matter. So the thickness of mat would increase the burning time. Okay, the greater burning time would be required, and basically, if we would then need to improve the water so that we could get a greater temperature difference basically between them, because conditions would become harsher for thicker glasses, and molecular composition. And I did tell you about the type of glass, right?
Yeah.
The type of class we by the way, we did check the type of class because the intention behind using the already broken bottle was to see that how that would have varied, because then the type had changed because they had strengthened basically due to the heat. So if you would have used a tempered glass or something like already thermo strengthened glass, so
Okay, thank you very much for that. I agree with you about this, and I would like to discuss also if you notice any anything different about the position of the knot. So where you knotted the string, was there any difference in
yes,
shape?
yes. Obviously, there was a difference because around the knot, the flame was basically circular around the knot. And at times at the knot, if it was angled at one direction, then the fire would be angled at that direction too, and so the localized heat was away from all the other string. I hope you understand what I'm trying to say. So at the knot, obviously it was not according to the rest of the cut. At the knot, we did have some imperfections, but using the number of loops, we did manage to limit that imperfection, because we would tie our knot between the loops, and so the flame wouldn't have been that spread out because of the knot. As for the like the fiber rope, that was too thick. We couldn't do anything about that, right? And it had a very intense flame. So for fiber rope, the knot, yes, that was a very big problem for us. So we couldn't do anything about that. But I hope that answers your question.
Okay. Did you consider maybe doing some cracks with, for example, a knife in the glass before, and some wavy structure, wavy curve with a knife on a glass before burning? And do you think this would affect the cracking of a glass?
So what you mean that first we crack the bottle and then we try to...
I'm sorry, yeah. So I mean that before cracking, you use a knife to get a tiny crack in the bottle, for example, like wavy structure, and then use a string to cut a more complex shape.
All right, now all teams can participate in the discussion.
Okay, so Mariam, would you like to answer this question?
Yes, definitely. Well, if I've understood your question correctly, then I think you're trying to say that did we try etching our design on the bottle with like a knife before and then wrapping the string on it? So have I interpreted your question right?
Yes.
Yeah. So we actually did consider that, especially for the variation part, because obviously, like getting a straight cut is pretty easy. But we kind of abandoned that idea since the problem statement, it only focused on, using a string. So we did consider that, but we did not end up experimenting that possibility because the problem statement kind of limited us to that point. But I do believe that if we already have some sort of a crack, then there's already some sort of stress present in the glass, and therefore it might just crack in the air because of if you don't put it in the water pressure, because the water does kind of cushion it all.
Okay. Thank you. Yeah, I agree. I would also like to ask about the profile of the glass. So if the glass had some curvature already on the surface, and would this affect the probability of cracking or the shape of the crack?
Yes. As for the curves, basically, what this would do, it would extend the area at which the flame would provide localized heat. Let's say if the bottle was like this, see, and the flame was at the bottom. So the flame would be the localized heat would be getting at this area, around this area, right? If the bottle is like this, so we'd be getting a crack on this area as well. So this was the thing with the curved bottles. Yeah, we did try that. Yes, we didn't put in the position, but this is I'm saying this because this is one of our observations. So I hope
Okay.
that answers your question. Is there
Okay.
any?
Okay. I would like to ask, when considering glass is a typical amorphous structure, so it doesn't have a crystal lattice. How does this phenomenon affect the cracking of the glass?
Could you kindly repeat your question? There was a distortion over there, so I couldn't really get your question.
So a glass is a typical amorphous structure. This means that it doesn't have a crystal structure because it doesn't have a long crystal planes in the structure. So why does this affect the outcome of the experiment? How would you see that in the experiment that the glass is actually an amorphous structure, not the crystal structure in this time?
I think that this phenomena in yeah, sure.
Okay. The thing is that the crystal structure might not have been able to build a temperature gradient, basically. So we would not have gotten the fracture because of the uneven expansion and contractions in the glass. That is why we get that localized heat type of thing. In a crystal, the heat travels uniformly, and the whole thing would have been heated. And even if we did put it in water, then we wouldn't have gotten a fracture because there wasn't this uneven expansion and contraction. So there wouldn't have been any thermal shock, and there wouldn't have been any temperature difference. So it is this property of glass is to fracture under thermal shock. I guess that answers your question, hopefully.
Okay, thank you.
And if you have any ambiguities, please do ask again.
We were thinking about the biggest curvature that one could get out of a glass in theory, and what are the limitations regarding this? What do you think are the limitations? So, in theory, how big of a curvature can you get out of the glass? You did some wavy structure, but how big waves which wavelength would be the biggest possible?
I think if you have a good fuel that provides good flame, right, and a material that burns in a good flame to provide good temperature, then I think any sine wave would do. The other waves, like a square wave or a triangle wave, because they have points, right? And at that point, we can't localize the heat, so it would eventually spread out. So we wouldn't be getting any smooth points, any smooth edges. But the sine wave doesn't have any edges or that sort. And if we get a good flame and the heat could be localized, so a sine wave could be. We could get a smooth sine wave out of it.
Okay.
May I start with a question? A question to the reporter. There is you proposed at the beginning of your presentation a lot of different explanation of the phenomenon, but no verification, no experimental verification of this theoretical approaches. So, did you do anything to verify that your theory is like conforms to your experiment? And if not, can you give me an example of an experiment you can conduct to verify the theory you have about the explanation of the phenomena and the experiment in question?
Basically, we did show that image which had the diagram labeled compressive on it. So they had two circles, right? The inner circle represented the inner layer of the glass. The outer circle represented the outer layer of that glass. So what we did was we lit the outer surface, so the temperature of the outer surface increased, but the temperature of the inner surface was cooler relatively than the outer surface. So when we put the whole thing in water, that temperature difference exaggerates because due to the temperature of the water. So the colder the water, the greater the exaggeration, and due to this this temperature difference, we get the fracture. So basically, this was the whole phenomenon.
Yeah, that's the whole phenomenon, but that's qualitative approach. I want like a quantitative approach. Like, how can you, with data, prove that what you're saying right now is true?
Okay, so for quantitative, I would suggest that if we measure if you could measure the temperature of the fire, and then we could measure the temperature of the water, then we could get the best temperature difference at which we would get the best sort of cut. So that should do. Basically, we had a limitation. We couldn't exactly measure the temperature of the fire. So that would be my experimental design to measure the. By that, we could also get. I mean, we could also get a clearer interpretation of the whole thing. I hope that satisfies them.
Thank you.
Okay, I think that's fine. Yeah. Other questions from other jury members too? So we can go ahead
yes,
first.
I have some. So to the reporters, when asked about the thickness of the glass by the opponents, you said that thicker glass would require more time to build a temperature gradient. And I mean, can you explain this in more detail to me? Why is that thinner glass builds up a bigger temperature gradient more quickly?
No, the thicker glass should have a greater temperature because due to the thickness, the inner surface would remain cooler, right, rather than the outer surface.
Okay.
So, did I say this? I'm sorry about that.
Okay.
But basically, the thicker glass should have a greater temperature difference because the thickness would be greater, right, and the inner surface would be cooler and the outer surface would be hotter. And since there is nonlinear transfer of heat, the temperature gradient would be greater in a thicker surface rather than in a thinner surface.
Okay, good. And about what you were just discussing, I mean, you've shown that some of the bottles cracked without before being put in the water. So why is that? Basically,
the material of this thing that we were using provided such a strong flame that the temperature gradient was too great that it didn't need to be put into water to exaggerate that temperature difference. The temperature, the buildup of that difference in temperature was great enough to fracture the bottle.
Okay. Okay. And sorry, go on.
Basically, why we put the bottle in the water was to exaggerate the difference, right? So if you have a good fuel which could give a good flame, so we wouldn't be needing the water anyways. But the cut was rough. Yes. So.
Okay. And why does the water exaggerate the difference between?
Because water has a colder temperature. Like the water is of like 3 degrees Celsius, and we put the bottle in it, so the cooler surface would get cooler, right? Instantly, it would get colder, and the temperature difference would be exaggerated like that.
All right, a question from Ivan. Please go ahead.
Yep, thanks. Now, a question to the opponent team. Will not ask only questions to the reporter. The opponent team, you brought a very interesting point at the last slide. What do you think will happen? like, or do you think the experiment will work if we have a 2D system? So we have a 2D glass and not a 3D, like not a bottle, but like you take a planar glass and you do the same experiment. Would it work better, worse? What's your opinion on that?
Okay. I think that if the string is placed in a straight line, for example, in a planar state, and the heat of the and the temperature of the and the heat transferred to the glass would be the same, I think that the process could be more efficient because there are no curvature, so maybe no